This talk presents the paper Learning to Extract and Use ASNs and Hostnames. This work is joint work between CADA and the University of Waikato. So the problem that we're working on is which autonomous system operates these three routers. When we observe a router in traceroute in the wild, often one of the first questions we'd like to answer is, which network operates that router? And there is a growing body of work that depends on getting the answer to this question correct. There has been recent work looking at patterns of interdomain congestion between networks, and clearly we need to understand who the networks are involved when we are examining interdomain congestion. Similarly, there's work looking at characterizing the cloud connectivity in the internet, as well as the effects of deployment of new cables on internet routing. And there are more examples described in the paper. So there has been a large body of work that is looking at router ownership inference techniques. And the property that they all share is that they involve judgment calls by their heuristic designers, their authors, and also that there is limited validation involved. So the first two papers by Morley Mao on this topic, the approach generally was to increase the congruity between a co-located BGP and traceroute view through prefix reassignment. They obtained validation from AT&T and they reported that in their paper. The next piece of work in 2010 by Brad Huffaker looked at a router ownership inference method that didn't require a co-located BGP view. For validation, they used a tier 1 network, a tier 2 network, and 5 research and education networks. In 2016, there were two techniques published at IMC, the border mapper technique, which looked to infer the operator AS for the first hop interdomain links that were observed by a vantage point. For validation, they used a tier 1 network, 2 access networks, and 1 RNE network. And the mapper technique, which as input used a large corpus of traceroute observations from multiple vantage points and inferred the operator AS of each through a graph refinement methodology. For validation, the author looked at the DNS hostname strings for 2 tier 1 networks and manually interpreted those and obtained validation data from 1 research and education network. And finally, the border map methodology that used heuristics from border map and mapit and synthesized them into 1 methodology. For validation, they used a tier 1 network, an access network, and 2 RNE networks. So what we can take from this is that the validation data tends to be focused around large tier 1 networks and research and education networks. So why is this question so hard in terms of which autonomous system operates a router? So it's particularly challenging to infer the operator of a border router because the router could have IP addresses that belong to their neighbors. The routers on the left-hand side, we've annotated those with their inferred AS number, and we can also see that for the first router, we might not even observe a interface owned by the AS that operates the router, in this case, AS15133. So border mapit, one of the heuristic methods, it uses a complex set of heuristics to infer the AS that operates the router. And they are basically formed into 2 groups. There is a graph refinement stage where what border mapit primarily uses is the AS ownership inferences of subsequent routers adjacent to the router in traceroute to reason about, in this case, router 2. So in this case, border mapit will infer AS3491 operates that router because it observes multiple routers subsequent to it also operated by AS3491, in fact, majority. For the other class of heuristic is based around routers where there are no adjacent routers subsequent in the traceroute path. And so for this class of routers, border mapit uses the origin ASs of destination IP addresses probed to reason about those routers. And in this case, this router is primarily observed in the path towards AS15133, and so border map it infers router 1 is operated by AS15133. So the approach that we investigate in this work is using information in host names and router host names to reason about the owner of a router. So the first thing to note is that operators often embed information in host names because it helps them to debug their networks. And so we would generally expect that while not perfect, it would be a reasonable source of information. In these routers, we can see that the operators involved have annotated things like the location of a router, the role of the router, and importantly for us, the operator of the router. So some operators embed the name of the network that uses their address. And this is the approach that Telia and Cbone both use to label routers operated by Edgecast and PCCW. And some operators embed the ASN of the neighbor network that is using their address. In this case, GDT does this. So it's well established that some host names in DNS are stale, often because these are manually updated by operators. So the question that we face with router 3 is the inferred AS incorrect, or is the host name stale? So broadly, the method that we use in this work is we focus on the routers with an ASN involved. What we do is we use heuristic inferences to label a training set. We use that labeled training set to automatically learn regular expressions that extract ASNs from those routers. And we do this through identifying that the AS number that we infer to operate the router is observed in a hostname string. We develop methods to automatically vet extracted ASNs that are different to inferred ASNs. So what we mean by this is that we distinguish between stale and correct host names. And then as part of a feedback loop, we can use the extracted ASNs to improve the heuristic inferences that border map it makes, that heuristic-based methods make. So there has been related work that has used hostname information recorded in the host names to reason about routers. So the first piece of work is the UnDNS piece of work. And what that broadly did was the authors handcrafted regular expressions through manual interpretation of host names. And they would identify the meaning of different components of a hostname string. So for example, that first regular expression up the top of the slide, that regular expression extracts the type of the router, whether it's a backbone or a gateway router, as well as the location. The rules for UnDNS also include a dictionary of mappings from a location, in this case to their role, to their geographic location. So following on from this, Brad Huffaker developed the drop technique, delay-based router positioning. And what that approach did was infer regular expressions that extracted apparent location identifiers, such as airport codes, from host names for routers. So as input, they used measurements of round trip time and topological distance between known landmarks and vantage points to automatically infer regular expressions that seem to extract those location identifiers. And last year in IMC, we published a paper that inferred regular expressions that extract apparent router names from host names for routers. So a router name is a string that is common between host names that belong to the same router and unique to that router. And the goal of this was to be able to use the host names to reason about router aliases when router alias techniques were not usable on those routers because the router either didn't respond to probes or didn't behave in the expected way. In this work, we are inferring ASNs, and we use as input 3 different sources of data that is published that's contained in the Internet Topology Data Kit published by CADA. We use a file of IPv4 routers where the aliases are inferred by MIDAR and Mercator. We use a file of router ownership inferences, these router ownership inferences either use the router to AS assignment method that was published in PAM 2010, or the border map method that was published in IMC 2018, as well as a file that contains the host names for each router interface observed in the IDDK. So broadly, the approach by example is to generate regular expressions that learn to extract the ASNs. And we can see we have labeled green labels where the ASN in the training set and the embedded ASN are congruent, and red labels where the training and embedded ASNs are incongruent. So the approach is generally to build regular expressions that increase in specificity and accuracy over the course of a few stages. So in the first phase, we build base regular expressions, and these base regular expressions are generally built around structure and punctuation. They do not look at the character classes involved between those punctuation. They just broadly identify where punctuation is expressed in a hostname string. This is true except for the portion that includes an ASN, where we also include any literal characters that are not punctuation characters adjacent to the ASN, as in regular expressions 2 and 3, which we build through examining hostnames D, E, F, and G. The second phase is to merge regular expressions that differ by a single simple string. So in this case, we can see that regular expressions 1, 2, and 3 are nearly identical. It's just that 2 and 3 include the letters P and S. So we embed in a regular expression, in a new regular expression, the literal characters that differ between the two regular expressions, to build a regular expression that matches more host names but is structurally equivalent to, in this case, regular expressions 1, 2, and 3. In the third phase, we actually look at the structure, the character classes between punctuation, and we embed character class components in the output regular expression. And then finally, if a single regular expression doesn't cover all of the naming conventions that a suffix uses, then we build a set of regular expressions, a naming convention based around multiple regular expressions, and that is our output regular expression. In this case, our output regular expression consists of, or naming convention consists of 2 regular expressions. So in terms of evaluation, what we used were the router ownership inference methods that were used by the IDDK between 2010 and 2020. The first phase used the router to AS assignment method, and the second set used the border map inference methodology. The third set is from ParentDB, and this training set is manually labeled by operators in ParentDB. Some of them may be stale, but generally operators are incented to keep those entries in ParentDB up to date. So what we first can say is that when we apply our inferred regular expressions to the training set, and we look at the congruity between the extracted ASNs and those inferred with the heuristic method, is that the conventions, the inference methodologies have made progress. So to start with, if we look at the regular expressions that we classify as good, and these are those where the heuristic method and the training and the ASNs and the host names have a positive predictive value of 80%, and we extract at least 3 unique ASNs congruent with that training set, then there's 3 times as many conventions using border map it than router to AS assignment for any given IDDK, right? Because we can see that the range of good regular expressions where we get 12 to 22 using the router to AS assignment method, with border map it, we're getting between 41 and 55. There are a set of naming conventions that we infer to be promising, and these are where the positive predictive value is greater than 50%, and there are at least 2 unique ASNs congruent with training data extracted from the training set. We classify these naming conventions as usable because they usually extract the ASN that operates the router. And in total, across all of the IDDKs and ParentDB snapshots, we inferred conventions, usable conventions for 206 suffixes. The other important point to notice here is that the number of suffixes that we're detecting embedding in ASN is increasing over time, so it's likely that this methodology that we introduce in the paper is going to become more useful over time. The final challenge, though, that we faced in using regular expressions is that some organizations only embed their own ASN, even for addresses they assign to their neighbor router. So what the operator here is doing is embedding their own ASN on resources they control, even though those resources are provided to neighbor routers. So we can detect these because the only ASN that's congruent, we only extract a single ASN that's congruent with training data, in this case AS15576. Hostnames D, E, and F, we can clearly see are assigned to customer routers. The operator of NTS is identifying that as such in the hostname record. And this makes up roughly half of the networks that embed an AS in a hostname string. So this is an important case to filter out. We validated 4 of the inferred naming conventions with 4 network operators, and they all confirmed that we captured their convention, and there is details in the paper about this. And then finally, we looked at the agreement between the training and the hostnames embedded in the ASNs embedded in the hostnames. So with the router to AS assignment methodology, the positive predictive value between the ASNs in the hostname and the training ASNs was between roughly 75 and 80%. With border map-it, the PPV was between 84 and 87%. And with parent UB, the agreement was 96%. So what we take from this is that we can hypothesize that while there are some host names that are stale in the sets that we examined with router to AS assignment and border map-it, it seems that more are correct than stale, and the heuristic methods that we used were inferring the wrong ASN. So we developed methods to vet ASNs and hostnames, and the paper describes this in more detail. But essentially the approach is that if we have a router R1 in this case, where the inferred AS is 555, and we have a hostname associated with that router that indicates it's operated by AS681, we will accept that hint if we see that if that ASN is that of a subsequent router, or if that ASN originates a destination prefix that we observe R1 in the path towards, or it's a provider AS of a AS in set A or set B. So this heuristic increased the congruity between inferences and host names in the January 2020 IDDK from 87% to 97%, and we validated whether the degree to which we could distinguish stale from correct host names, and we found that this simple heuristic was able to select the correct host names for 92.5% of the host names that we had in our validation set, which covered roughly 2/3 of the incongruent host names. So where we see this work headed towards is a more evidence-based router ownership inference methodology, because again, the validation that the heuristic techniques used was anywhere between 1 and 7 different ASs, primarily focused around tier 1 ASs and RNE networks. Our set of regular expressions covers, in the January 2020 IDDK, 90 different ASs of different size and location and roles. So we publicly released the source code implementation of our inference methodology for inferring regular expressions. We publicly released those inferred regular expressions, as well as web pages that show how each regular expression applies to the training data. And the screenshots on the left-hand side of this slide show what you can roughly expect on those web pages. And we publicly release our extensions to border map-it to vet the ASN annotations and integrate them into border map-it inferences. So this is what I have to talk about for this paper. If you have more questions, please send me an email. Thank you.